So let us talk about heat exchangers in this video. Before solving questions, I'll be giving you some short notes about heat exchangers. And the main two types of heat exchangers that we generally analyze are parallel flow heat exchanger and counter flow heat exchanger that we generally study, okay, for GATE. So let's start with parallel flow heat exchanger. So parallel flow heat exchanger. Parallel flow heat exchanger. In this heat exchanger, what happens that the hot fluid and the cold fluid flow parallelly. Okay. So let THI be the inlet temperature of hot fluid, THO be the outlet temperature of hot fluid, TCI be the inlet temperature of cold fluid, and similarly TCO be the outlet temperature of cold fluid. Okay. So what will happen that the hot fluid will give its heat to cold fluid. Okay. So one of the important concepts that we use while solving questions is energy conservation. Okay. Energy conservation. I'll write here. We'll use it often in the questions. You will be given THI, TH0, TCI, and you will have to find TCO by using energy conservation. Or you will be given 3 temperatures out of these 4 temperatures, and you will be finding the 4th temperature using this energy conservation. Okay. So this hot fluid has some specific heat capacity. Let it be CPH, and similarly, this cold fluid is also having some specific heat capacity. Let it be CPC. CPC. Okay. Now CPH and CPC, this is small c, okay? Small c, CPC are specific heat capacities. Specific heat capacities. Okay. Let there be a mass flow rate m dot h, that is the mass flow rate of hot fluid flowing in this tube, and m dot c is the mass flow rate of cold fluid. Okay. So m dot h CPH will denoted by capital C H, that is heat capacity of hot fluid, and m dot c CPC is equal to CC. This is capital C, this is denoted by capital C, heat capacity of cold fluid. Okay. So what is more important now, that when these fluids flow, they will exchange heat. Okay. The hot fluid will give its heat to cold fluid. Okay. So if I construct the temperature distribution of hot fluid and cold fluid with this length x, it will be like this. You must have studied it when you will be studying you must have studied this heat transfer. So it will be like this, that the hot fluid will continuously lose heat and the cold fluid will continuously gain heat. Okay. This temperature is THI, that is the inlet temperature of hot fluid. This is TCI, inlet temperature of cold fluid. This is THO, that is outlet temperature of hot fluid, and this is TCO, outlet temperature of cold fluid. Okay. So this will be the temperature profile. Okay. Now let's move on to the second type of heat exchanger that we study for gate. That is counter flow heat exchanger. Parallel flow heat exchanger in which both the fluids move parallelly. Okay. Now in the counter flow heat exchanger, counter flow heat exchanger, counter flow heat exchanger. Okay. If the hot fluid moves in this direction, the cold fluid will move in this direction. So that means now if this is THI, that is inlet temperature of hot fluid, this will be TH naught, but here this will be TCI, that is inlet temperature of cold fluid, and this will be outlet temperature of cold fluid. Okay, so this is counter flow heat exchanger. Okay. Let's draw the temperature profiles of the fluids moving in the pipes. Okay. So again, the hot fluid will lose heat, and this heat will be gained by the cold fluid. Okay. This will be like, yeah. These are not straight lines. Okay. These are curved lines. So now this will be TCI. This will be TC naught or O, outlet. This will be THI, inlet temperature of hot fluid, and this will be THO. Let me tell you an important point here, that in case of parallel flow heat exchanger, the maximum temperature of the hot fluid that can be dropped is up to here only. Is up to this outlet temperature of cold fluid. Okay. You cannot drop the temperature of outlet temperature of hot fluid below the outlet temperature of cold fluid. Okay. In a parallel flow heat exchanger. But in case of a counter flow heat exchanger, this does not apply. The temperature, the outlet temperature of hot fluid can be below the outlet temperature of cold fluid. Okay. In the case of counter flow heat exchanger, not in the case of parallel flow heat exchanger. Okay. Also, the irreversibility generated, the entropy generated in case of parallel flow heat exchanger is more as compared to that in counter flow heat exchanger. We'll also solve a question, and we'll prove this, that for the same temperature reduction, the area of counter flow heat exchanger will be less than the area required for the parallel flow heat exchanger. Okay, I'm not going to derive it because it is a crash course, so I'm giving you just important points regarding this. Okay. So this is the temperature profile. Okay, now what we have to do further, we have to, so there's a term defined which is LMTD. LMTD. What is this LMTD? Written as log mean temperature difference. Why it is used? Because the temperature of both the fluids is continuously changing. Okay, the temperature of hot fluid is changing, cold is changing. Cold is changing. Here the temperature of hot fluid is different. Here the temperature of cold fluid is different from this point. Okay. So what we do is we take a mean temperature difference, and for that the formula is, which you have to remember, LMTD is equal to delta T1 minus delta T2 upon ln delta T1 by delta T2. Okay. This can be delta T2 minus delta T1 upon Ln delta T2 by delta T1. Okay. So what is delta T and delta 2 now? Delta T1 or delta T2, whatever you want to denote, in case of parallel flow heat exchanger, is the difference between the inlet temperature of hot fluid and the inlet temperature of cold fluid. So this is delta T1. Okay. And delta T2 is similarly the temperature difference between the outlet temperature of hot fluid and the outlet temperature of cold fluid for a parallel flow heat exchanger. Similarly, in case of counter flow heat exchanger, this will be delta T1. That is the temperature difference between the inlet temperature of hot fluid and outlet temperature of cold fluid. Okay. And delta 2 here will be the difference between the temperature of hot fluid, outlet temperature of hot fluid, and the inlet temperature of cold fluid. Okay. So generally we use this temperature profiles to find out delta T1 and delta T2. Okay. We'll solve some questions regarding this. So LMTD is same for the LMTD. The formula of LMTD is same for parallel flow heat exchangers and counter flow heat exchangers. Okay. Obviously, when we'll be solving some questions, we will get to know that LMTD for a counter flow heat exchanger is more as compared to the parallel flow heat exchanger. Okay. So this formula is same for both, for parallel flow heat exchanger and counter flow heat exchanger. Okay. Then next, what we have to discuss. There are some special cases that we can discuss. Special cases. Special cases. There are two special cases. First, when a fluid is undergoing phase change. Okay, when one of the fluids is going a phase change. Phase change. And the second one is when the heat capacities of hot fluid and cold fluid are same. Okay. That is capital CH is equal to capital CC. This second case is applicable only in case of counter flow heat exchanger. So I'm writing here. This second case is applicable. Second case is applicable only in counter flow heat exchanger, denoted by this sign, counter flow heat exchanger. Okay. So let's discuss the first case when one of the fluids is undergoing a phase change. So when one of the fluids is undergoing a phase change, such that in a steam condenser or steam generator, that is boiler. Okay, let's draw the temperature profile of the fluids. Suppose this is a temperature profile for a condenser. Okay, so steam is condensing. This is a THI, inlet temperature. This is outlet temperature, TH0. Okay, the steam is condensing. That means its temperature won't change. That is why a straight horizontal line. Okay, but on the other hand, we have a cold fluid whose temperature will be increasing. Why? Because steam is condensing. That means it will be giving heat, and that heat will be absorbed by this cold fluid. So TCI, TC0. Okay. Yeah. This is for steam condenser. This temperature distribution is for steam condenser, and for steam generator, that is boiler. Now this hot fluid THI, TH naught, TH naught, TCI and TC naught. So this hot fluid will now be giving heat to water and it will be converted into steam. Okay. So this will be losing heat and this water will be gaining heat, but it is undergoing phase change, so temperature will remain same. Okay. This is a case of boiler. Boiler. And this is condenser. Okay. So you must have proved it when you must have studied heat transfer, that in both the cases of parallel flow heat exchanger and counter flow heat exchanger, whether this is parallel flow or whether this is counter flow. Okay. If I even draw this and make it as counter flow. Okay, this is counter flow heat exchanger in case of boiler I have drawn, and this is a parallel flow heat exchanger in case of condenser I have drawn. You take whatever case, parallel flow or counter flow heat exchanger, the LMTD in both the cases will be same. The LMTD in both the cases, LMTD in both the cases, both the types of heat exchanger will be same. So if you're given a question that a steam is condensing and some other data is given, but nothing is given about whether this heat exchanger is parallel flow or whether this heat exchanger is counter flow, do not get stressed out, because in both the cases, whether you take it as parallel flow or whether you take it as counter flow heat exchanger, LMTD will be same. Okay, it will give you the same value when one fluid is undergoing a phase change. It doesn't matter uh, if it is a counter flow heat exchanger or if it is a parallel flow heat exchanger. Okay. So the second special case is when the heat capacity, okay, not the specific heat capacity, the heat capacity, that is the product of mass flow rate into specific heat capacity. Okay. So the heat capacity of hot and cold fluid are same. In that case, LMTD is equal to delta T1, second case, which is equal to delta T2. This is applicable only when the heat exchanger given is counter flow heat exchanger. Okay, be careful, only for counter flow heat exchanger, not for parallel flow. It is not applicable for parallel flow heat exchanger. Okay. And in this case, the temperature profiles will be straight lines. Okay, this is THI, this is THO, this is TCI, and this is TC. This is delta T1 and this is delta T2. Okay, so this delta T will always remain same in case of counter flow heat exchanger when the heat capacities of hot fluid and cold fluid are same. Okay, so this is a very important and special case. Very important case. Special case, very important. Many a times the question have been asked on this case and in various examinations also. Okay. So LMTD is equal to delta T1 is equal to delta T2. Yes, it is equal to this temperature difference in this case. Okay. So this we have discussed. We have discussed both the cases now. Let's move on to next portion, that is NTU. So NTU. What is NTU? NTU is number of transfer units. And what does it signify? Number of transfer units. It signifies the area of heat exchanger. Okay, so it signifies the area of heat exchanger. Area of heat exchanger. Okay, and this NTU can be less than 1, can be greater than 1, or can be equal to 1. Okay. So this can be greater than 1, this can be less than 1, this can be equal to 1. Okay. But generally, this NTU is not greater than 18. Okay. This is not greater than 18 generally in practical applications. This is not greater than 18. Okay. However, can be less than 1, it can be equal to 1, it can be greater than 1, but generally in practical applications it is not greater than equal to 18. Okay. It's greater than 18. Okay. So and there is a formula that you have to learn for this NTU, which is UA by sorry, C minimum. Now what is this UA? U is the overall heat transfer coefficient that you know. A is the total area of heat exchanger that is available for heat transfer between the two fluids. Okay, and C minimum is the minimum heat capacity. This is the minimum heat capacity, whether it is of cold fluid or of hot fluid. So what you do is you find heat capacity of cold fluid, you find heat capacity of hot fluid, and whichever is the minimum, that will be C minimum. Okay. So this is the formula for NTU, number of transfer unit, and signifies the area of heat exchanger. Let's move on to the next part, which is effectiveness of a heat exchanger. These are just short notes. Okay, so effectiveness of a heat exchanger. Effectiveness of a heat exchanger is actual heat transfer upon maximum possible heat transfer. Okay, actual heat transfer is what? Actual heat transfer will be either it will be m dot h cph delta t h, that is the temperature change of hot fluid, or it will be m dot c cpc delta tc, that is temperature change of cold fluid. Okay, that is, this is the heat lost by hot fluid and this is the heat gained by cold fluid. This will be actual heat transfer. Okay, so this will be the actual heat transfer. What about the maximum possible heat transfer? So can I say that Q max possible is equal to C minimum, that is heat capacity rate which is minimum in both the fluids, delta T maximum. Okay, so let's talk about why we are taking C minimum here. Because heat capacity is what? Heat capacity is the heat required to raise the temperature of the fluid by 1 degree Celsius. So if this is minimum, that means the heat required to raise its temperature by 1 degree Celsius will be minimum. So that is why we are using C minimum. Okay. And maximum possible heat transfer will be possible when the temperature difference between both the fluids is maximum. So that is why delta T maximum. Okay. And delta T maximum will be equal to THI minus TCL. This is the maximum possible temperature difference in a heat exchanger. Okay. That is the inlet temperature of hot fluid and the inlet temperature of cold fluid. The difference between the two is the maximum available temperature difference in a heat exchanger. Okay. So this is about maximum possible heat transfer. But generally what we do is, when we write this, effectiveness is equal to, this is C minimum Thi minus Tci, and in the numerator part is Q actual, which is m dot HCH, or let me write it in this way. Let me write it in this way, that heat capacity of hot fluid CH delta TH, or CC delta TC. So effectiveness is written this way. But what we do is, we try to write that part in numerator which has C minimum. If CH is equal to C minimum, we will write this term only. Why? Because this C minimum will actually get cancelled out by CH. So we will get the effectiveness in terms of only the temperatures, and the calculation will be easier for us. Okay. So it's written in this way. Now after solving, we also have two formulas for effectiveness. One is for parallel flow heat exchanger and the other is for the counter flow heat exchanger. Do learn them because they are useful from examination point of view. So effectiveness for a parallel flow heat exchanger is equal to 1 minus e raised to the power minus NTU 1 plus C upon 1 plus C. Okay, I'll tell you what C is. And for counter flow heat exchanger, it is 1 minus e raised to the power minus NTU 1 minus C upon 1 minus C into e raised to the power minus NTU 1 minus C. So difficult formula, but do remember it. Let me check it also. Yeah, I know I've written it correctly, but let me confirm it also. It's a difficult formula. Yeah, it is 1 minus C e raised to the power minus 1 minus C. It's correct. Better to check it than give you a wrong formula. So you learn it properly. So it's correct. This is for parallel flow heat exchanger, the formula of effectiveness, and this is for counter flow heat exchanger. Okay. What is this NTU? NTU, you know. What is this C? Capital C. Capital C is C minimum upon C maximum. Okay. That is the heat capacity ratio. C is the capacity ratio. Capacity ratio. Okay. So if two fluids are flowing, we are dealing with only two fluids. So one will be C minimum and the other will be C maximum. But be careful that it is the ratio of C minimum upon C maximum. This is capacity ratio. Okay. Next is what? Next is okay. So again we have special cases here. Special cases. And the special cases are same. That is, when one fluid is undergoing phase change, and the second one will be that the capacity ratio of hot fluid and cold fluid are same. Okay, same, equal. That's it, equal. Okay, so in a phase change, can I say that this capacity ratio will be 0? Why? C minimum by C maximum. Okay. So when a fluid is undergoing a phase change, its heat capacity ratio will be what? It will be infinity because the temperature is not changing and it is taking heat. Okay, so C max goes to infinity, and that implies heat capacity ratio will be 0. Okay, so when you put this C0 in these two formulas, what you will get? See, this will be 0, this will be 0, so it will be 1 minus e raised to power minus NTU in case of parallel flow heat exchanger. In this case, it will be, this is 0, so this whole term becomes 0, this is 0. So again, in this case, you get 1 minus e raised to power minus NTU. That means when a fluid is undergoing a phase change, when one of the fluid is undergoing a phase change in a heat exchanger, the effectiveness of both parallel flow heat exchanger and counter flow heat exchanger is same, and which is equal to 1 minus e raised to power minus NT. Okay, 1 minus e raised to power minus NT. Okay. Yeah. So let's move on to the second special case when CH is equal to CC, that is heat capacity of hot fluid is same as is equal to heat capacity of cold fluid. Okay. So in this case, the capacity ratio C is equal to CH by CC or C minimum by C max, and it is equal to 1. Okay. This becomes 1 because CH is equal to CC. In this case, the second case. Okay. C minimum is CH, C maximum, whatever. Both are equal. So this becomes 1. So now in this case, when you put C is equal to 1, in case of parallel flow heat exchanger, what do you get? You get 1 minus e raised to power minus NTU. This is 1. That is 1 minus e raised to power minus 2 NTU upon 2. Okay. So effectiveness for a parallel flow heat exchanger when the capacity ratio is equal to 1 will be 1 minus e raised to power minus 2 NTU upon 2. Okay, this is the case. What happens when you put C is equal to 1? In the formula of effectiveness for a counter flow heat exchanger. Okay, this is 1. This becomes 0. E raised to power 0 is 1. This is 0, and this is 1. This is again. This is 1. This becomes 0. This becomes 1. 1 minus 1 is 0. 0 upon 0, that is undefined. So what you do is you actually use L'Hospital rule and derive an important formula in the case of counter flow heat exchangers. Counter flow heat exchangers. Do not get confused by this CH or CC. I've just written it, okay? Let me remove it. So in case of counter flow heat exchanger, this will be when after you apply L'Hospital's rule, the effectiveness formula comes out to be NTU upon 1 plus NTU. Okay, this is the formula. Okay, so this is the formula for the in case of counter flow heat exchanger for effectiveness when the heat capacity of hot fluid and cold fluid are equal. And next is what we can discuss. I think we have discussed all the things. NTU I have told you, and effectiveness, yeah. So these are just the what you can say short notes or short information about heat exchangers, and using this information we'll be solving some questions in the next video, and I guess I've covered almost all the important formulas that are useful for GATE and almost all the important concepts in a short video. So in the next video we'll be solving some questions using this formula to learn them thoroughly. Okay, this thanks.